All right, folks. Well, I'll introduce Michael Koenig. He's the project leader of Honda Smart Home. The American Honda Motor Company Environmental Business Development Office. He's been a part of a project that's been local. You might have heard a lot of press about it, seen some of the online articles. Michael is part of Honda's Environmental Business Development Office. He moved from auto R&D in Ohio to Los Angeles 3 years ago to join the new group and to become the project leader for the Honda Smart Home in Davis. We thank you for coming today. Mr. Michael Koenig.
Great. Thank you. So I think this was originally scheduled for 45, but I'll try and wrap up by 2 so we can get back on the schedule.
Absolutely.
Get everybody to the airport or wherever. Thanks very much. This is about the Honda Smart Home, which we did in Davis, California. It's a 1944 square foot single-family home. We located at UC Davis West Village in large part because it's planned to be one of the largest zero-net communities, and we thought if we're looking towards the future, then that situation, that scenario, that energy profile on the grid is more like what we'd like to see in the future. So that was a large part why we located there. And the user, the occupant of the vehicle, is going to be able to use the house, and also a Fit EV all-electric vehicle comes with it as a package. The rest of this, the 2020 goal for zero net energy, I think everybody here knows that. And some of the thoughts are, how do we get there as a society? It's easy to say it, but there's a lot of work that needs to happen to get to that point. So this is our chance not only to demonstrate one vision for how to get there, but also for us to have this laboratory, this living laboratory where we can fiddle with it, we can take data, we can do some R&D work. First question usually is, why is Honda doing this? Honda Motor Company, yes. Because as a company, we're focused on more than just mobility. And frankly, as a society, we need to look beyond just your transportation, because your personal carbon footprint is probably a third of it due to your daily commute if you have a conventional IC car. And within the U.S., probably 44% of your GHG emissions for the nation are between your home and your car. So if we're serious about climate change, we need to look at both of them, and we recognize that. So right now it's very convenient and reasonably cost effective. Honestly, in a lot of places, you can put solar panels on your roof, you can put a battery electric vehicle in your garage, and you have a zero carbon footprint. You can do it right now and not really suffer. So why not? Well, the trouble is, and I'm an outsider to the energy industry, and as such, I have the freedom to make my own assumptions. And from the outside, it looks like there's at least 4 big troubles with ubiquitous distributed generation solar panels on your roof. There's backflow issue, there's the duck curve everybody's heard about, there's the intermittency and flicker, there's voltage rise through the day. So we see these in the future. Will you actually be able to get an interconnection agreement signed by your utility? If you've got 5 or 10 or 50% penetration on your feeder, is everybody going to actually be able to get that interconnection signed off by the utility? Without some changes, I think the answer is probably no. And similarly with battery electric vehicles, we'd love to have one in every garage, but there are troubles, more obvious troubles. And so we think that by combining these technologies and thinking about them and using their strengths, we're able to come up with solutions instead of troubles. So why are we doing this? Well, this is a demonstration of a vision for how we can get there. And I should say that we realize there are a lot of smart people working in the space, the people looking at each of these problems, and there are a lot of different good ideas, aggregation of vehicle charging, aggregation of electric water heaters. There's all sorts of good ideas for how we can move forward. We had a specific solution here that we're demonstrating. How can we get to this future without causing strain to the electrical grid? And then the second part of this project was about sustainability more holistically, because we talk about energy a lot, and I realize this is a ZNE conference today, but it's not just about energy. If you care about trees and air and water, you need to think about those things. It's not just a question of energy. So today I want to go through 2 things. First is there's 3 kind of interesting technical systems in the house that I wanted to go into a little bit of detail on, and then a few slides about sustainability. So first big technical system, of course, is the home energy management system. It's kind of the heart of what it does that's new and different. And there are a couple guys that sell similar things off the shelf already. We built our own in order to give us a lot of flexibility to do almost anything. So the system is a 9.5 kW solar array on the roof, and that's actually more than we need for the house and the car. By calculation, we should have maybe 20% surplus. So it's a pretty big array with a little bit of overhead, a little bit of headroom. It's a 10 kilowatt bidirectional inverter, AC-DC, DC-AC, with a 10 kilowatt DC car charger. I'll show you in a second. The way it's set up in the garage, here's the inverters in here, batteries here, and the car chargers here on the wall. And it's a 10 kilowatt hour, 10 kilowatt lithium battery that we have parked next to it. I should mention down at the bottom of the slide says, play the video, go to hondasmarthome.com. This presentation has some embedded videos, and so if you're on the webinar, I can't guarantee you're actually going to see them, but on the website, we've got probably a dozen different videos. We also have all of our plans are open source, so if you want to look at what we did, the architectural plans are there, the 2D data, 3D data is there, the MEP system's there if you want to look at our HVAC system. All of our specs or countertops or light fixtures, everything is there available, and we will be dumping all of our data on that same site in the future. So looking at the house in general, the solar panels, of course, on the south side, and solar panels make DC power, the car uses DC power, and so one of the considerations for the system was to try and keep it DC as much as possible. So if you're home during the day, plug the car in, we're going to take that DC power, just do DC-DC conversion, charge the car directly from solar. The reason, of course, is you can change AC to DC and DC to AC, but you lose a few percent every time you do it. So we try to keep it DC. So if you're not home, what we'll do is we'll just store that power in the stationary battery during the day, get those nice and charged up, and then when you come home at night, we'll just discharge the battery and charge the car, because normal daily commute is a little bit less than 10 kilowatt hours of energy for most normal drives. Other thing it can do is addressing the issue of intermittency and flicker. Is it's great in Davis we get a lot of sunny days, but clouds move over, the voltage drops, but instead of letting that flow out as variation in our power flow, we'll just automatically dispatch the batteries to discharge, make it up, smooth out all the power so that the utility doesn't see that variation just because our production wavered. And then we can understand what's going on the grid 3 different ways. We can just look at the voltage online right now. We can look at the Cal ISO site and see what should be online through the day over the next 24 hours. Or we can actually receive OpenADR signals through a gateway box and respond if tomorrow is going to be a demand response day. We can plan for that. And then kind of intelligently use the power. We can push it if there's a need. We can pull it if there's a need. Or if we know, for example, we're going to have to charge the car by AC, maybe it was a cloudy day, we didn't get enough DC power today, we're going to charge the car by AC, I can look and say, when is going to be the cleanest power online? We can charge the car using the lowest carbon footprint grid power. So here it is in the garage. The left side is actually inside the house. In the mechanical room in the house, we have this industrial controller because it's a prototype system with a lot of energy. It doesn't rely on a Mac Mini. You know, we could have controlled it with very low computing power, but it's an industrial controller we're using. The second system is the heating, cooling, and hot water system, which is very, very cool. UC Davis Western Cooling Efficiency Center put this together for us, and actually Davis Energy Group was the MEP of record, so Dick is representing both today, I think. The system is neat for a number of reasons. One is Davis is like Sacramento. It's kind of desert climate, so it gets really hot during the day in the summer, but it cools off at night. And so we can pre-cool the house, save on our air conditioning loads by just pulling in cool air at night every night that it cools down. It is 100% radiant heating and cooling. We don't have any conditioned forced air at all. We're using the same wide bore Helix ground source heat pump, and it's a single heat pump, so it's heating and cooling and hot water coming from the one machine. We don't have any burner, we don't have any backup elements in the hot water tank. It's only a storage tank. And then I'll show you in the next video, heat recovery was one of the things we were really interested in, and so I'll show you how we try to minimize that waste. If you're a HVAC nerd, and I know some of you are in the audience, I thought I would show the schematic of it. You can see heat pump tied to the domestic hot water. We also do have a DC preheater in cooling mode, so we can pull the waste heat out. 2 zones for the second floor ceiling and the first floor in the slab. It's a 2-ton heat pump, by the way. We figure we only need about 1.5 tons, but it's a 2-ton machine. So here we go. The mechanical room sits right in the middle of the house, and it has on the floor is the little Bosch 2-ton machine, and next to that is the hot water tank. It's a tank-in-tank design, so it looks like a really big tank, but there's probably only about 70 gallons of potable water in it. And then next to it is a mass production off-the-shelf drain heat recovery unit. If you've not seen these, they're very, very cool technology. So usually what happens, you take a nice hot shower, you get all this hot water running down the drain and out to the sewer, and you just lose all that energy. The drain heat recovery unit is just a heat exchanger that's wound around the drain pipe, and so the wastewater naturally clings to the walls of that pipe as it goes down. So the incoming cold water that's coming back to refill the hot water tank gets preheated as it runs through that drain heat recovery unit. And then the wastewater flows out. But instead of going to sewer, 4 of our boreholes are wetted, so we can actually take that gray water and run it out. And Dick alluded to this. This is more complicated than what he was doing in his project. We actually have a sealed system for our gray water. That gray water flows in and then overflows out to irrigation. But in the process, we've got in here the coils, the force side coil, so we can exchange energy. We can pull the nice preheated fluid, take its energy out, send it back to the heat pump, and then obviously mechanically compress and make more hot water, send that back into the hot water tank. So we do actually recover some of that heat from the gray water. Of course, we have valves on the system, so we can just switch the valves and send all that hot water to the floor or to the ceiling to condition the house to heat the floors and the ceiling. And then since it's reversible, we can cool the house the same way. We do need to watch dew point on the second floor, but we can cool the house radiantly. And then, of course, cooling means that we're pulling heat out of the house. So again, with the desuperheater now, we can recover some of that heat that otherwise would be wasted, because we can now, if the tank is available, we can send some of that rejected heat to the hot water tank. The university was interested in a number of things. The wide bore, yeah. Nice. That's a good question. That's one of the questions. Oh, sorry. The question was, are we able to get enough cooling capacity from the radiant panels in the house? Right, exactly. Especially cooling. That's one of the big questions. We added some additional tubing in the master bedroom, because that showed that it would be a little bit sketchy. So we get a little bit more capacity in the master. We actually have it on a horizontal wall as well as the ceiling. But one of the questions and one of the investigation items is exactly that: what's the actual thermal comfort in the house? The hope is that in cooling mode, we're getting natural convective currents off the ceiling, and so it's flowing down, but also that the mean radiant temperature is more readily available. But that's certainly one of the questions. Downstairs, for sure, it's cool and comfortable, and it actually can be a little uncomfortable if it gets so cold underfoot. So one of the things that the university was interested in is those wide bores, and PG&E is interested in. So we have a ton of data going on. We have the 4 wetted boreholes that I mentioned, but we actually have 4 dry boreholes. We figure we only need about 4 total, but we've got 8, 4 wet and 4 dry. And we've got thermocouples in the wells, of course, in the fluid flows. We've got the volume of fluid flow being measured. But then we also have midway between boreholes, we've got Christmas trees of thermocouples down in the earth. So Dick had mentioned about the dearth of data over the next few years. We'll be generating a lot of data coming out of this. So if anybody's interested to see how much energy is coming in and out of the earth, and how much, macroscopically, how does the earth temperature drift over time, or what's the difference between the top couple feet and the bottom couple feet, we'll have all of that data getting published. One of the other things that the university was working on was this aerosolized sealant. So trying to achieve the tightest envelope and the lowest HVAC energy consumption, one of the techniques is, you can manually caulk every stud bay, and you can manually go around and fill all your gaps, but that's labor intensive, and not everybody does that very well. So they're looking at this aerosolized technique where you pressurize the house, fog it with this mist, and then the mist finds all the cracks on the way out. It's pretty interesting. And then to your question exactly, that was one of the questions that they were interested in investigating is what's the actual performance of the three-mode heat pump and then the comfort of it. So the secret sauce is there's no secret sauce. The whole package was designed holistically, trying to get a lot of details right, and it starts with the fundamental design. So we have this really efficient HVAC system, this really small HVAC system, because the package, the envelope is so tight, because the envelope is well insulated, because we oriented it east-west, we put slightly higher solar heating coefficient glass, triple pane all around, 0.16 U-factor windows. We also use double stud walls. Ours are 9¼ inch cavity depth, full filled with cellulose, and are 60 in the roof. So trying to get all of the details right about passive design before we put solar on the roof, before we put an HVAC system in the backyard, including things like the overhangs, right? So we spend a lot of time to model these overhangs and make sure that they were optimized so that in the summer it's easy, but in the summer they're shaded, but then in the winter that they're basically fully exposed. So these are just a couple screen grabs. Daylight simulation on the winter solstice showing how much free light and free heat we should be getting out of those windows. But the punchline is down here at the bottom. We should be using about 75% less energy than a Title 24 house built in Davis, which is something like 3 megawatt hours annually, which is about as much energy as the car uses. So we can drive the car all year just on the savings from our HVAC system, which of course means the envelope, but also the equipment. Here's the holes going in. We actually had a pretty cool telescoping drill rig. I didn't get the top of it in the photo, but the drill rig was only probably 8 feet tall or something like that, and it telescoped down. This might actually be Dick standing here, putting the slinkies going down in the hole. The wet holes were a bit more complex, but that's what they look like. We use this kind of, it's like a pipe you use for culvert as the vessel. Here's the panels going in, and I mentioned we ended up actually adding a little bit of loop on the east side wall in the master bedroom, and then here's what it looks like in the ceiling. So the entire cathedral ceiling across the south side of the house, and then the flat ceiling on the north side of the house all has this radiant tubing, and it's in this metal pan so that the heat is more evenly distributed on the drywall when you put the drywall up. Then the last technical system that I wanted to mention is the LED lights. So it's 100% LED, all very high CRI, all very comfortable off the shelf, with one exception, LED lights. And, you know, lighting is getting better and better and better, and Title 24 is obviously requiring more and more efficiency. But it's easy to still have lousy lights in your house, and so one of the things we wanted to promote and just have a conversation about, because, you know, honestly, we're lucky. If some random guy had just built the exact same house, he wouldn't have gotten any media coverage. It would have just been, oh, you know, Bob built a house, whatever. We're lucky because, oh, it's interesting, Honda built this house, and so we get a lot of coverage, and so it's an opportunity for us to talk about these things. You know, Honda's not in the lighting business, but it's an opportunity for us to have conversations like this and say, if you're going to build a really efficient house, it shouldn't be about sitting in the dark in a cave. It should be a better experience. We should be smart enough to build better and more energy efficient homes and systems. And so the lights are an example of that. This is far and away the nicest lighting of any place I've ever lived. And in part, it's because we have these nice controls. We've got daylight controls, so, you know, lights don't come on if it's bright enough already. We've got motion sensing, so lights don't come on unless you walk in the room. And then 5 different times a day, we do different things. If you walk in the kitchen at 6 o'clock, you're probably making dinner. All the lights come on. It's bright. It's beautiful. If you walk in the kitchen at 9, you're probably getting a glass of wine. We only just light up the tabletop, you know, the countertops, and it's really, really pleasant. If you're walking around at midnight, you're probably just finding your way to the bathroom. We've got these very low hemisphere, deep amber safety lights all around the house, so we don't bleach out the rhodopsin in your eyes that are helping you navigate the house. So we tried to make this be a very, very comfortable living environment. And then, of course, you know, you do things automatically. Sometimes it's not right. So we do have override switches on the walls so that if it's not what you wanted, you can just turn the lights on or off on them, you know, with a switch. One thing that I did want to mention is we worked with the university's California Lighting Technology Center to try to be as compatible as possible with your natural circadian rhythm. So your body has a 24-hour clock, and it's sensitive to a lot of things, including, it turns out, blue light. So the dashed line here in the graph is your circadian sensitivity to the blue light spectrum, which is unfortunate because that's exactly where a lot of LEDs have a lot of energy, a lot of CFLs have a lot of energy there, and your eyes really aren't that sensitive to it, so you don't see that well by this light, but it does disrupt the production of melatonin. So if you're at night, you're using your laptop, you've got an LED on or CFL on, and you've got a lot of blue light content, your body's going to stop making melatonin, and then you're going to have a hard time going to sleep. So tried to respect that by having very warm colors. Everything in the house is actually fixed with very little blue light content, except there's a clear story, like a plant shelf up here, that we have a dynamically color changing linear array, and so we can have bright blue light earlier in the day and then to warmer oranges in the evening. And then all of these controlled with tablet applications, so you can manually override these things. You can see what's going on. I can watch in real time what's my solar production or what's my home consumption to try and get feedback. And the second part is I promised a few slides about sustainability because I am interested in energy, but I'm also a green building nerd at heart, and so it's an opportunity for us to talk about all of these other things. So for me, the cat's meow for sure is cradle to cradle. If you haven't read Bill McDonough's book, read it because it's the way that it makes sense about how you can rationalize what it means to be sustainable. In order to try and break things down, I'd like to think of it as kind of 5 elements of sustainability, one of which is energy, but we also need to think about water and waste and occupant health, which usually is indoor air quality, and then the materials themselves. So I'll talk about a couple of these here. Water, of course, very high priority, and it starts with design. If you turn your faucet on and have to wait for 5 minutes to take a hot shower, you just wasted 5 minutes worth of water running down the drain. Very basic, and that is exactly the amount of volume that's in the pipe between your hot water tank and your shower. So make the pipe as small as possible, make the run as short as possible. So you saw in that video with the drain heat recovery, you saw that the showers were directly above the hot water tank. That was intentional. The kitchen sink is right on the other side of the hot water tank so that we have the shortest runs possible. And then, of course, low flow fixtures, dual flush toilets, what you'd expect. And we don't use turf. There's just not enough gray water to irrigate it, and we made the decision early on that we wouldn't use any potable water for landscape, so we only use gray water, and we use drought-tolerant plants. And then just to kind of respect the natural environment, you'll see these rocky swales here. These are the gutters, so we run the roof water down and maintain it 100% on site. We don't let it overflow into the streets, into the city sewers. And we end up with about 1/3 of the total water consumption of a normal house. Portland cement, you might know, you might not know. Portland cement is one of the biggest greenhouse gas contributors globally, something like 5%, depending on whose numbers you look at, because it's made from limestone. And when you convert it to cement, it breaks apart and releases carbon dioxide. But to do it, you need to get it up a couple thousand degrees, so you burn a bunch of natural gas to get it up. And so it's about 1 pound of CO2 for every pound of Portland cement that you produce. So what we did was we actually you can use fly ash or some other things. We used a naturally occurring volcanic ash, this pozzolan material. It's overburdened from some mining operations in Nevada. You can take this stuff. You can actually offset more than we did. We offset 50% of our Portland cement was replaced with this pozzolan material. And then also, the original slab design was something like 10-inch thick monolithic slab with a bunch of steel rebar in there, which obviously uses a lot of material, uses a lot of steel. So we changed that to a post-tension slab, thinned it down by about half, and then just use half as much material. Here it is getting installed. I don't know if you can see the bent ones down here are actually the polyethylene tubes for the radiant heating and cooling in the slab, and then the straight black lines are the tendons getting ready to be set in the concrete before the post-tensioning operation. And then at the end of the day, we polished it, and this, again, is just, I don't want to say smart because it seems like you're ringing your own bell, but it's just kind of smart green building is if you can polish a concrete slab, you don't need to use any flooring material. And then also, since it's radiant, it just radiates heat more effectively because we don't have any insulative cover on it. Right under the sofa, where your feet are, we have very thin carpeting, but the rest of it on the first floor is exposed concrete. All of the wood in the house is Forest Stewardship Council certified for sustainable forestry. All of the trim, the furniture, everything that we used a lot of lumber, it's all FSC certified. And then just just honestly, to talk about it, instead of using rigid foam, visitor center is more conventional optimum value or advanced framing techniques. It's 2x6s, 24-inch center, conventional frame in the visitor center. But instead of using rigid foam board, which is kind of the normal building science practice on the exterior, we use cork because it's totally sustainable and it's kind of baked together. It doesn't even use exterior glues to hold the stuff together. Just as a conversation, because the production of these rigid foam boards have a pretty high greenhouse gas potential from the blowing agents, and then the end of life, you have the same cradle-to-cradle question of, what do I do with this foam board at the end of life? How do I reuse it? How do I separate it from my structure? So we use cork. So wrapping up here, what are we doing next? Here we are in the mechanical room, the heat pump, the hot water tank, and then here's the manifold. So all of our hot and cold water runs through here. And these little black specks here on each of the pipes are individual meters. So all of our pipes are home run. All of them are metered, so we can tell exactly how much water is going exactly where. All of the circuits, we use more circuits than we need. We've got maybe 40 circuits so that they can all be individually metered, so we can tell where the energy is going. We've got thermocouples in the floor, the bottom of the floor, in the middle of the slab, near the top. We've got them through the wall, so you can see heat profiles through the wall. So as I said, we've got them outside. We've got temperatures of the fluids moving. We've got outside weather conditions, solar radiance, solar power being produced, all being collected about 270 channels at 1 minute resolution. So we'll dump those as probably about 60 meg files per month, something like that. So we'll start publishing those here, starting with April 1st data. Just for giggles, just threw a couple plots in so you can see the kind of data. You can see kind of fun things like the refrigerator, how regularly it cycles until it has a defrost cycle or whatever's going on there. Or you can see solar production, nice. Oh, crazy solar production day because it was a little bit cloudy. So we have civilians living in the house. As part of the requirement for that community, they have to be associated with the university. So we have university staff member living there with her family, a family of 4. And as I said, we're going to be publishing the data. PG&E is a partner here, so PG&E actually is going to be publishing some studies of that also. We'll have our own data, and then we'll just have the raw data also get published. And we'll be there at least 3 years. So we have a maximum 10-year commitment, but a minimum of 3 years that we'll be there operating and have different families live for a year at a time. So that's what I have. We have 5 minutes maybe? The questions?
There's one question online. Who designed the house? Who designed the lighting?
The lighting was UC Davis California Lighting Technology Center. We also had an interior designer from Davis area called Mac, who was involved in some of the fixture selection.
Any other questions?
You can design a net energy home, but once you put an occupant in there, the human factor really can change the dynamics, more importantly, the performance of that home. Have you already seen or been able to trend specifically that the energy consumption by design versus influence of the human behavior in that home itself?
That's a good question. That is something we will be doing, but it is not something I've done yet. So I've only started looking at the data starting now. We've been doing a lot of work with the telemetry to make sure that all the data was consistent. And so some of the previous data sets, if you have even a few hours or a day of data where the data is a little funky, then it kind of mucks with the analysis. But that's definitely something we will be doing here, just to compare our assumptions with what we're doing.
Yes, Dick?
So, Michael, one of the really great things you did with your couch at the visitor center was let people learn a little bit about it and know it's occupied. Can you say a little bit about what's going to be in there and what the accessibility of that is?
Sure. The question was, what is the visitor center? What can it do, or how would you get in? If you're in Davis area, you're certainly welcome to stop by. The house is located literally just behind the Energy Efficiency Center at UC Davis West Village. There are mixed-use buildings there. The ground floors are offices for the Energy Efficiency Center, and right behind that building is the start of the single-family homes, and the smart home is the first home in that neighborhood. So if you go to the Energy Efficiency Center, you can borrow the key to the visitor center and let yourself in. The content in there, are you able to see hidden slides or no?
Ooh, I don't know.
I might have a hidden slide that has a picture of the visitor center in there. Scroll all the way down to the bottom. Inside the visitor center, there are, there you go. Make that visible. Inside the visitor center, there's 3 little kiosks that let you play with the lights and the lighting colors and just see what does it mean to have these different colors. You can see real-time displays of what's going on in the house and play with the controls. And then the center kiosk lets you either play videos, there's like the technical animations, the live action videos, and then there's a way to just look at the schematics of the house on it. Honestly, almost all that content is available on the website. Visitor Center has a little bit more, but not so much. But if you're there, you're certainly welcome to get the key and get inside.
I've bring in terms of already there's different thermal masses.
The biggest difference, honestly, is in the cooling mode to monitor the dew point. So we do have to only run the first floor. Sorry, the question was, what's the strategy for first floor versus second floor? We do have to throttle back or shut off the top floor to make sure that we don't ever get close to dew point. And then just the difference between the first and second floor and the energy moving in and out of the tubes, we have adjustable pump flow, so we're targeting a 10-degree delta T coming and going through the start to end of the loops. So I haven't looked at that to compare, but I would wager that there probably is a difference in the pump flow between first and second floor to maintain that.
Right, but then let's say in California, on that cool morning, we have a lot of concrete slab, right? Does that affect the concrete house?
Yes, and that was certainly part of the design strategy, was to build it with a lot of thermal mass because it is such a small system and because there are kind of rapid, large and rapid temperature changes through the day. So part of the strategy is exactly to allow it to coast. We do operate, the thermostat does operate based on air temperature. We'll look ahead to see if tomorrow's going to be hot as to whether or not we pre-cool the house, with the outside air. But as far as the operation of the heat pump goes, we'll run it based on a regular thermostat air temperature.
I just wanted to point out one more thing. It's a great article in Washington Post. A friend of mine in Denver sent me a copy of, because it apparently also appeared in the Denver Post. Oh, congratulations.
I think so. That was a surprise, and that was the first time that the occupants got interviewed. So luckily, they had positive things to say.
That worked out. All right. Well, great. Thank you very much, Michael.
Thank you.
Okay. Up next, we have Marco Alves.